Continuing on with Unit 10, this is the first part of Learning Target 10B. So Learning Target 10B is going to be all about simplifying square roots, and in this video we're going to talk about how to simplify a single square root, how to multiply square roots together then simplify, and also how to divide square roots and simplify, and if needed we will also be rationalizing the denominator. Let's start with our first property here. So the multiplication property of square roots says for if I have two values, a and b, which are greater than or equal to 0, then the square root of the product of those two, so the square root of a times b, is equal to the square root of a times the square root of b. So what this means is if I have a product of numbers inside of a square root, I can break them apart each into their own individual square root. And on the vice versa, if I have a product of square roots, I can also multiply them together underneath one single square root. And the reason this is helpful is we actually will use both directions of this. We'll use this forward direction here from the one square root into breaking it apart into multiple square roots if we have any perfect factors or perfect squares we want to factor out. And then we'll use the reverse of this if we start off with a product of two or more square roots. How can we simplify those together? So let's look at our first couple examples. So for all these examples, it says simplify the following. And example 1, 2, and 3 are all kind of review problems from us from past units. Why don't you guys pause the video right now and simplify down example 1, 2, and 3 on your own first, and then we'll check those together. Okay, so to check, let's start with example 1. So when we're looking at these numbers, we want to be doing a factor tree on these and thinking about any perfect square factors that are inside. So remember, our perfect squares are 1, 4, 9, 25. Oh, I missed 16. 1, 4, 9, 16, 25, 36. All of these are perfect squares because they can be rewritten as a base to an exponent squared. So for example, 4 is the same as 2 squared, 3 squared is our 9 value, 4 squared is our 16, 5 squared is our 25, and 6 squared is our 36. Now of course there's an infinite amount more depending on what we make our base. You might be wondering, well, why is 1 on the list? Well, 1 squared is the same thing as 1, so it is a perfect square as well. And we want to keep in mind what are our perfect square factors that are hidden inside that we can factor out. When I look at 160, immediately I'm noticing that I have 16 and 10. Since 16 times 10 would give us 160. Now there's other ways to factor 160, but I'm looking for our largest perfect square factor, and 16 happens to be that value. So using the multiplication property, what this means then is I can break apart the 160 as 16 times 10 using the factors, and from here I can distribute kind of the square root and have the square root of 16 times the square root of 10. So I can break apart using that multiplication property of square roots for us then. From here, I can simplify down the square root of 16. The square root of 16 is equal to 4, and then the square root of 10 has no other perfect squares inside of it, so our final answer then would be 4 times the square root of 10. Let's look at example 2. So example 2 says the square root of 72. So when I'm looking at 72, I'm looking for all those perfect square factors that are inside of it. One of them that I notice is 36 and 2. Now, if you factor 72 a different way, that's fine. Just make sure you are factoring all of the perfect square factors out. So 36 is the largest perfect square factor, so I can rewrite the square root of 72 as the square root of 36 times 2, which we can then use the multiplication property of square roots and break this apart into the square root of 36 times the square root of 2. Notice the operation here does not change. 36 times 2 is what I began with, so I end up with the square root of 36 times the square root of 2. From here, the square root of 36 will reduce down to be 6, and the square root of 2 cannot reduce any further since 2 is a prime number, and I end up with 6 times the square root of 2. Now, technically, you could rewrite these in either order, so you could write the square root of 2 times 6. Normally, in most textbooks, you won't see it written this way. We usually tend to put the integer coefficient in front, And the reasoning behind that, or at least that I think is behind that, is it's really easy to accidentally maybe extend the square root too far, and the 6 is no longer inside that square root, so we want to make sure that they are two separate terms that are still multiplied, but the square root is only over the stuff that is left over inside. So in this case, the square root of 2. So if you're going to rewrite them in this order, I would suggest that you're putting parentheses around it to really signify what part is still within the square root and what part is out. I'm going to be writing all of the answers with the stuff that I've taken out of the square root in front. But that is an equivalent answer. Let's look at 3. So 3 says the square root of 99. So when I'm thinking about factoring 99, I'm looking for the largest perfect square inside of it. I notice that 99 is the same thing as 9 times 11. So I could rewrite the square root of 99 as the square root of 9 times 11, break that apart using our multiplication property for square roots, and we get the square root of 9 times the square root of 11. Square root of 9 is going to be equal to 3, and then square root of 11 cannot simplify down any further since that is a prime number. Notice that once I took the square roots of all of these, so once I took the square root of 16, the square root of 36, and the square root of 9, the square root symbol goes away because I've applied that property now. So I don't end up with the square root of 3 in this example, I end up with 3, since the square root of 9 is equal to 3. Let's look at example 4. So starting with example 4, we're going to start to build in our variables as well. So in example 4, we have the square root of 12 times x to the 8th. We've dealt with how to simplify square roots of numbers, so we can tackle the square root of 12, and we've also talked about how we can simplify variables inside square roots. We're just putting these two concepts together. The first thing I'm going to have us do on these is break this apart and deal with the square root of the number part, or the coefficient, and then the square root of the variable. So I'm using that multiplication property of square roots to break it apart into the square root of our coefficient times the square root of our variable. The reason I'm having us do it is it's a little easier to handle each of these problems individually. Why don't you guys pause the video and simplify down the square root of 12 part. Just simplify down that piece. So when we think about factoring 12, we have 4 times 3, so we're looking for the largest perfect square that's inside 12. To break this apart, we would get the square root of 4 times the square root of 3, and then the square root of 4 we know is 2, and I end up with 2 times root 3. That's all coming from the square root of 12 piece. To simplify the variable part, I want to think about what the square root really means. So back in a prior unit, I'm going to do this in a separate color as kind of a review up here, we talked about radical form to exponential form. And we learned that if I have the nth root of, let's say, x, that's the same thing as x to the 1 over n power. Remember that n there is our index, and we can go from radical form on the left to exponential form on the right, and vice versa. So we can go back the other way. In this section, we're dealing with all of our roots, or all of our radicals. Oops, there's a C in radical. There we go. R-I-C. Sorry, that got a little messy. We're dealing with all of our roots here being square roots. So our index in all of these is going to be equal to 2, since I have nothing written and they're square roots. So I can rewrite these all as the base to the 1 over 2 power. We're going to do that on the x to the 8th, so we can think about how this simplifies down. So I can rewrite the square root of x to the 8th as x to the 8th to the 1/2 power. We also learned at the beginning of, I believe it was unit 7, our properties of exponents. So if I have a power to a power, I can multiply those. So 8 times 1/2 would give me 4, and I would end up with x to the 4th then. This only worked out though because our power was divisible by our index. So this worked in this case because the power, which was equal to 8, is divisible by our index, which is equal to 2. And this will work in some cases quite nicely. We are going to look at some examples about what happens if that doesn't work and how we have to kind of factor the variable piece of this. But in this example, since our power here, which was 8, is divisible by our index of 2, then I can simplify this down perfectly and end up with no more x's inside the radical sign. So our final answer, I'm going to group terms that are outside of the radical together, and I'm going to group anything that is left over inside the radical together as well. So outside of our radical, we have 2 and we have x to the 4th. So I'm going to write our final answer as 2 times x to the 4th, and then the square root of 3 is the only thing left over inside. And that will be our final simplified answer. I am going to ask that you guys take down to this final step of combining anything in front of the radicals together and combining anything that is still left over inside of the square root together as well. Let's look at example 5. In example 5, it says the square root of 54x to the 7th. So I'm going to do the same thing we did on example 4 and break this apart as the square root of 54 times the square root of x to the 7th. Why don't you guys pause the video and simplify the square root of 54 piece on your own first. Okay, let's check how we can factor 54. So there are perfect squares hidden inside. The largest perfect square is going to be 9. So I can break this apart into the square root of 9 times the square root of 6. The square root of 9 will then give us 3, and I still have the square root of 6 left over. Now for the variable piece, my exponent this time is 7. So I have a power of 7 and an index of 2. So I could rewrite this as x to the 7th to the 1/2. The issue though is in example 4, 8, our power here was divisible by 2. But in example 5, 7 is not perfectly divisible by 2. So instead I have to think about, well, how can I break apart 7, x to the 7th, in order to have a piece that is divisible, the largest piece that is divisible by our index of 2, and then anything that is left over. So I'm going to do a factor tree on x to the 7th. The largest piece that I could break that apart would be x to the 6th, because the next integer value under 7 that's divisible by 2 is going to be 6. That would leave me then with a single x left over. So I could rewrite x to the 7th then as the square root of x to the 6th times the square root of x. And the reason this is equivalent is because when I multiply exponents with the same base, remember we add the exponents together, and 6 plus 1 would give us back to that 7 that we started with. From here we can simplify the x to the 6th. This would be the same thing as x to the 6th to the 1/2 power, and I still have the square root of x left over. When I have powers to powers, remember we multiply them. So 6 times 1/2 would give us x to the 3rd. So we're going to end up with, I still have the 3 square root of 6 times now an x to the 3rd times the square root of x. Now for our final answer, we want to combine anything that is outside the square roots together and combine anything that is inside the square roots together. So in this piece, the stuff that is outside the square roots is going to be the 3 and the x to the 3rd. So I can multiply those and get 3x to the 3rd. And then inside the square roots, I have the 6 times the x. So we'll end up with 6x inside the square root. And this will be our final answer. We know that this is simplified all the way down because the 6 has no more perfect squares inside of it. So I can't factor anything out of the square root of 6. And on the variable term, the reason I know that we are done simplifying here, and I'm going to add this in red on the side, is we are done simplifying the variable. There we go. The variable. So we are done simplifying the variable when the power is less than the index. And I want to fit that on one line, so let me scoot the word power over. So when our power, or our exponent that's left over, is less than the index. So in this whole section, we're just dealing with an index of 2. So for all of these problems, my index is going to be 2. So I'm looking for any variables that are left over inside the square root to have a power that is less than that index. So our power then would have to be 1, and in this case this does work since I have an x to the 1st here. So that power here of 1 is less than my index of 2, so I know I've simplified the variable as much as I possibly can. Let's look at example 6. So in example 6, it looks a little bit different. We now have a variable and actually a coefficient, a -1a multiplied in front. Well, that's fine. That's just something that's multiplied already outside of the square root. I'm going to leave that alone for a little bit. Let's look at the rest of the piece. We have the square root of 80 times a to the 9th. So we can break this apart into the square root of the number piece times the square root of the variable piece. Why don't you guys pause the video and simplify the square root of 80 on your own first, and then we'll check it together. To simplify 80, I'm going to think about factors of 80. So 80 factors as 16 and 5, because I want to look for perfect squares. So 8 and 10 is 1, but neither 8 or 10 are a perfect square. So I want to look for the largest perfect square inside, which would be 16. The negative a is going to go along for the right. It's going to stay in front. It's going to be multiplied to the square root of 16 times the square root of 5 by breaking apart that 80. Let's look at the variable piece now at the same time. So I have an a to the 9th. So what is your power here and what is your index? Our power here is the 9 and our index is the 2 from the square root. Is our power divisible by our index? In this case, our power is not going to be divisible by our index, so I need to break apart this a to the 9th. That does not look like an a. There we go. I need to break apart this a to the 9th so that I have a piece that is divisible by my index, and I want it to be the largest value. So how could I break apart a to the 9th to have something that is the largest thing that would be divisible by 2, and then the stuff left over? To do that, it would be an a to the 8th, since the next integer value under 9 would be 8, and 8 is divisible by 2, and then this a to the 1st that is left over. And again, the reason I can do that is because when I'm multiplying these bases, I'm adding the exponents, and 8 plus 1 would give me 9. Breaking apart the a to the 9th, I end up with the square root of a to the 8th times the square root of the single a left over. Now that we've broken it apart into all these different terms, let's simplify down what we can. So the negative a is still there. Square root of 16 is a perfect square, so I end up with 4. Square root of 5 cannot be simplified, so I still have the square root of 5. And then the square root of a to the 8th, I can rewrite this as a to the 8th to the 1/2. And then the square root of a is still left over. Power to power tells me I need to multiply them, so I end up here getting an a to the 4th power in place of that a to the 8th to the 1/2. And then everything in front, I'm going to start combining these. So I have a negative 4a from the first two terms, square root of 5 still, times a to the 4th times the square root of a. Our last step is to combine anything that is outside of the square roots together. So I have a negative 4a and an a to the 4th. When we're multiplying bases, we have to add the exponents. So I'll end up with a negative 4 still, a to the 5th, since I have one of them plus 4 of them. And then for my square root that's left over, I have a 5 times a, and so I end up with the square root of 5a. And that whole thing will be our final simplified answer. And again, we know we simplified it far enough because the square root of 5 is a prime number, so it can't simplify down any further. And then our exponent here, which is 1, or our power on a is 1, and that is less than our index of 2. Let's look at example 7. So in example 7, we have negative 3x to the second power times the square root of 12x to the third. I want you guys to try example 7 on your own first, and then we'll check it together. Let's check example 7. So I'm going to rewrite the negative 3x squared, since that's outside of the square root. I'm going to break this apart into the square root of 12 times the square root of x to the third. Now 12 factors is 4 times 3, so we can break this apart as the square root of 4 times the square root of 3 by doing a factor tree here on 12. Now the x to the third, our power here is 3 and our index is 2, and since 3 is not divisible by 2, I also kind of need to factor or break apart this x to the third. The largest factor inside would be an x to the second, since 2 would be divisible by 2, and I'm left over with this extra x to the first. So I end up with the square root of x to the second times, the square root of our single x. So what I've done in this first step is just broken apart the perfect factors or perfect square factors inside 12 and inside x to the third. Simplifying this down, we still have the negative 3x to the second. Square root of 4 is going to give us 2. Square root of 3 is still there. And then the square root of x to the second will give us a single x back. And then the square root of x is still stuck inside since I can't simplify that anymore. Our last step here is to combine anything outside the square root. So the negative 3x squared, the 2, and the x. I'm multiplying all these together, so I'll end up with a negative 6 from the negative 3 and the 2. X to the second times an x will give us an x to the third, since I'm adding the exponents. And then in the last piece, I'll multiply the stuff inside the square root, which will give us 3x. And we end up with negative 6x to the third times the square root of 3x as our final answer. Okay, let's look at example 8. So in example 8, we have 5y times the square root of 32y to the 6th. Why don't you guys pause the video and do example 8 on your own first as well. Let's check example 8 together. So the 5y is just going to go along for the ride for a little bit. I can break this apart into the square root of 32 times the square root of y to the 6th. 32 is not a perfect square, but if I factor it, 16 times 2 would give us 32, and 16 is a perfect square. So I can rewrite the square root of 32 as the square root of 16 times the square root of 2. On the square root of y to the 6th, my power this time is 6, my index is 2, and 6 is divisible by 2. So there's no need to break this apart, and I can just rewrite this in exponential form, and then I'll end up multiplying those and I'll get a perfect divisible value. So simplifying this down, the 5y is still there. Square root of 16 is going to be 4. Unfortunately, the square root of 2 cannot simplify anymore. And then y to the 6th to the 1/2 will end up giving us y to the 3rd by multiplying those. Last step is to combine anything outside of the square roots together. So the 5y, the 4, and the y to the 3rd. When I multiply these together, 5 times 4 will give us 20. Then y times y to the 3rd will give us y to the 4th. And the square root of 2 is the only thing left over inside that square root. So we end up with 20y to the 4th times the square root of 2. So in these first 8 examples, we looked at how can I simplify when I have variables underneath the square root. And what we're really looking at is how can I break this apart? If our index is, or if our power here is divisible by our index, then I can just divide them out. So in this y to the 6th to the 1/2, I was able to divide them and get y to the 3rd. But in a case where my power here is not divisible by the index, so in example 7, we had this x to the 3rd, and since 3 is not divisible by 2, we have to break this apart. You guys are probably noticing that what happens every time is I drop down one power, so I have my x to the 2nd, because that will be an even value, and I'm left over with a single x to the 1st every single time we have an odd exponent. So because our index here is always going to be 2, if our exponent on our variable is even, they'll perfectly divide out. If our exponent is odd, I have to break apart or kind of peel off a single x to the 1st, and I'm left over with the extra x to the even powers then left over, which will simplify part of that down. In the next couple examples, what we're going to look at is, well, what happens if I have now a product of 2 square roots? So I have 3 times the square root of 6 times the square root of 18. There is more than one way to do all these types of problems. The approach that I'm going to take is if there's anything that's a nice perfect square or kind of a more obvious perfect square inside, I'm going to simplify those first and then multiply together and see if I can continue to simplify. Another route would be to just multiply anything that's inside of the square root to begin with and simplify from there. Personally, I prefer to simplify what I can to begin with on each individual piece so that I'm dealing with smaller numbers overall. So let's look at example 9. We have 3 times the square root of 6 times the square root of 18. So 6 has no perfect squares, so I'm going to rewrite 3 times the square root of 6. I'm going to write a little bit smaller so I have enough space. But the square root of 18, I know that 18 factors as 9 times 2, and 9 is a perfect square. So I'm going to break this apart into the square root of 9 times the square root of 2. From here, The 3 root 6, again, I still can't simplify anymore, but the square root of 9 is 3, and I'm left with 3 times root 2 then. Just like we were doing before, anything that's in front of the square roots, I'm going to combine together. So 3 times 3 is going to give us 9. And then anything inside of the square roots, I want to simplify. So 6 times 2 would give us 12. Now we've combined it down into one term, so I don't have other things multiplying that I could combine together, but I want to make sure it's fully simplified. And the way we know if it's fully simplified is if the stuff underneath the square root has no more perfect squares inside of it. So I'm left with the square root of 12. Is that fully simplified, or is there stuff that I can take out of that square root? So in this case, I can actually continue to take stuff out. So 12 factors is 4 times 3, and 4 is that perfect square. So I can break this apart as 9 still times the square root of 4 times the square root of 3. Square root of 4 will give us 2. I'm still left with the square root of 3. Our final answer then, if I multiply the 9 and the 2 to get 18, I'll get 18 times the square root of 3. So in these problems, we can see that although we're simplifying each piece on their own, once I multiply them together, there might be more simplification that has to keep happening. And so we want to make sure that if there's anything we can continue to simplify, we make sure we simplify it all the way down. Let's look at example 10. So in example 10, I have the square root of 2a times the square root of 9a cubed. So we're introducing variables back again, but that's okay. We've tackled them before. Let's look at what I have here. Is there anything to you guys that jumps out as a perfect square right away? What I'm noticing is the 9. So the square root of 9 is a perfect square. So I'm going to rewrite the square root of 2a, and then I'll break that apart into the square root of 9 times the square root of a to the third. I can simplify down the square root of 9 to get 3, and then a to the third does have perfect squares inside of it, but I'm going to leave it alone for now because it's not a perfect square itself. Instead now, I'm going to multiply the stuff that's underneath the square roots together. So the 2a and times the a to the third. The 3 will stay in front, so I'll end up with 3 times the square root of 2a to the fourth. We want to make sure that this is fully simplified. So we have two pieces here. We have the 2 and the a to the fourth. Is there anything here that we can continue to simplify down? In this case, the variable can keep simplifying down. And the reason I know that goes back to what we talked about earlier. We are done simplifying when the power that's left over inside is less than the index. And our power here of 4 is bigger than our index of 2, so I have to keep simplifying this. When I break this apart, I still have the square root of 2. Then I end up with the square root of a to the fourth. Now when we were simplifying variables, we're looking to see if our power is divisible by our index. Is our power here of 4 divisible by our index of 2? In this case, they are. So I can rewrite this as a to the fourth to the 1/2. Multiplying those, we end up with a to the second. And our final step is just combine stuff that is outside of the square roots together. So the 3 and the a squared to get 3a squared times the square root of 2. And that will be our final answer. Let's look at example 11. So in example 11, we have 2 times the square root of 7x times 3 times the square root of 14x to the second. Right now, are there any perfect squares that you guys are noticing here? The one perfect square I'm noticing is this x to the second power. So I can break this apart. I'll still have the first terms here. So 2 times the square root of 7x, still have 3, square root of 14, and then square root of x to the second. Since the square root of x to the seventh is a perfect square, I can simplify that down to just be a single x outside of the square root. So the square root of x to the second gives us x. From here, I'm going to multiply anything that's outside of the square roots together. So the 2, the 3, and the x, I'll end up getting a 6x. And I want to multiply the stuff that's inside the square roots together. So the 7x and the 14. When I multiply those, we end up with 98x. From here, we just want to make sure we're simplified all the way. So can I take anything out of the 98? Can I simplify down the square root of x anymore? What do you guys think? So the piece here that we can keep simplifying is actually the coefficient. So 98, if we do a factor tree over here on the side, is actually the same thing as 49 times 2. And 49 is a perfect square since it's 7 times 7. So we can break this apart and we still have the 6x. Then we're going to have the square root of 49 times the square root of 2. So this was the square root of 98 piece, and I still have that square root of x left over. And that square root of x cannot simplify any further because our power here of 1 is less than our index of 2. Last thing to simplify, square root of 49 is 7. So I get 6x times 7, square root of 2x. I'm going to go ahead and combine those back together since they're still left inside the square root. Final step, multiply anything that's in front of the square roots together. So 6 times 7 will give us 42. There we go. So we get 42x square root of 2x. And both the 2 and the x are left over inside the square root. So I want to make sure my square root is over both of them then. Okay, let's look at our last example on this page. We have 7 times the square root of 5x times negative square root of 20x to the 4th. So what I have here is I have a couple pieces that are in front of the square root. I have a 7 and I have a negative 1. I'm going to go ahead and multiply those right to begin with so that I accidentally don't turn this into a subtraction problem. So these are multiplied because of the parentheses there. So I'm going to go ahead and multiply the stuff in front right away. So I get the negative 7. Now when I look at the stuff inside, I don't really have any perfect squares that are jumping out at me. So I'm going to go ahead and multiply that 5x and the 20x to the 5th. When we do that, 5 times 20 will give us 100, and then x times x to the 5th will give us an x to the 6th power. Why don't you guys finish off this problem and simplify it, and then we'll check it together. Let's check example 12. So we multiplied the stuff in front to get the negative 7, then we multiplied the stuff underneath the square roots together to get 100x to the 6th. We can break this apart into the square root of the number piece. So the square root of 100 times the square root of x to the 6th. Both of these are actually perfect squares. So the square root of 100 would give us 10. And the x to the 6th, the square root of that is actually going to give us an x to the 3rd. And the reason I know that is because 6 is divisible by our index, which is 2. So I end up with x to the 6th to the 1/2. So our final answer, I'll have a negative 70. From the negative 7 times 10, and then the x to the 6th to the 1/2 will become an x to the 3rd. So in this last example on this page, we're saying that maybe we don't end up with a square root at all in our final answer if everything ends up being a perfect square. Let's look at examples 13 and 14. So we actually have 3 terms now. That's okay. I can put as many of these together as we want to because we're still going to apply the same properties. So on something like this, what I'm looking for is 1, do I have any obvious perfect squares to begin with? 6, 2, and 3, none of those are perfect squares. And then x to the 3rd, x and an x to the 5th, all of those are odd exponents, so none of those are perfect squares either. So right off the bat, I'm going to actually multiply everything and put it all underneath one radical. So I have 6 times 2 times 3. So I'll end up with a 36 then. And then an x to the 3rd, an x, and an x to the 5th. When I multiply those, remember we're adding the exponents. So I have 3 of them plus 1 of them, plus 5 of them, and I'll end up with x to the 9th then. So we took this problem that looked very complicated to begin with since I had 3 of these square roots multiplied, but I can just multiply all the stuff underneath the square roots together by using that multiplication property, and it condenses down nicely to be the square root of 36 x to the 9th. Why don't you guys pause the video and finish off simplifying example 13 because we can simplify this further. So to simplify this further, 36 is a perfect square, and then so the square root of 36 will end up giving us 6, and then the x to the 9th piece. So when I have this x to the 9th, 9 here is my power that's not divisible by my index of 2. So I need to break this apart into the x to the 1st that's left over. That will be left over inside the square root. and then the x to the 8th. The reason I'm doing this is because 8 is an even number. It's divisible by my index of 2 this time, and I can simplify down the square root of x to the 8th further by rewriting it as x to the 8th to the 1/2. Oops, that was a 1/2. That looks like 7 over 2. To the 1/2, and then the extra x to the 1st is still inside the square root. When I have power to power, we multiply them, and we get 6x to the 4th times the square root of x, and that will be our final answer then on example 13. Hey, why don't you guys pause the video and try example 14 on your own first, and then we'll check it together. So on example 14 here, we have -3 times the square root of 10x to the 3rd times the square root of 2x to the 3rd times 4 times the square root of x. So what we're going to do is multiply anything that's in front of the square roots together. So the -3 and the 4 will give us a -12. And then for the other pieces, I'm going to multiply all the stuff that's left over inside. So 10 times 2 will give us 20. I have an x to the 3rd times an x to the 3rd times a single x. So I'll end up with an x to the 7th then inside that square root. From here, I want to factor as much as I can. So 20 factors as 4 and 4 is a perfect square. So I'll have the square root of 4, square root of 5, and then the x to the 7th we can break apart as x to the 6th times an x to the 1st. So I'll have the square root of x to the 6th times, the square root of x. Let's clean that up. Hi, from here, let's simplify our perfect squares. So the -12 is still there, square root of 4 will give us 2, square root of 5 is still there, and then the square root of x to the 6th, since that power is divisible by our index, I'll end up with an x to the 3rd there. From the x to the 6th to the 1/2. So combining everything, I get a -24 square root of 5 times an x to the 3rd times the square root of x. Last step I need to do, anything in front of the square roots, I'll multiply together and group. So I have a -24 x to the 3rd, and anything inside the radical, I'll multiply, and we'll end up with a 5x. Again, we know we're simplified all the way because 5 has no perfect squares inside of it, and our power here on our x is less than our index of 2. So we are done with example 14. Okay, let's look at, our division property. Sorry, scrolled all the way back up to the top. So our division property for square roots is very similar to what we did with multiplication. So for this one, we're assuming that a is greater than or equal to 0, and b is strictly positive. And the reason b won't equal 0 here is we're actually dividing by b, and we don't want to divide by 0. That's not valid in a math course. What the division property tells us is if I have the square root of a divided by b, I can break that apart into the square root of a over the square root of b. Sometimes it's helpful to do this forward direction and break it apart if a and b are perfect squares, or sometimes we want to reverse it and actually combine stuff together and then simplify down before breaking it apart. So let's look at some of these examples. 15 says the square root of 64 over 49. I'm going to go ahead and break this apart into the square root of 64 over the square root of 49. And the reason being is 64 and 49 are actually both perfect squares. So when I do that then, now that they're individually each inside their own square root of 64 is 8, square root of 49 is 7, and I end up with 8 over 7. And that would be our final answer. Remember, our goal in all of these is we'll probably end up with fractions. That's going to happen. And we're still going to probably end up with square roots, but our goal is to get rid of as much outside of the square root as we possibly can. So although maybe we could divide 64 and 49 to start with, we really want to break these apart since both 64 and 49 are perfect squares. Let's look at example 16. So example 16 says the square root of 8x to the 3rd divided by 50x. Well, what I'm noticing here is that I don't have any perfect squares. 8's not a perfect square, x to the 3rd is not, 50 and x are not perfect squares either. So I'm going to reduce down the fraction as much as I can and see if we get some perfect squares. So 8 over 50 would actually give us 4 over 25. And then x to the third over x, remember when I divide exponents with the same base, I end up subtracting, when I divide powers with the same base, I end up subtracting their exponents, so we get an x to the second in the numerator. Let me make sure I have enough space here. So I'll end up with 4x to the second over 25 then. And all of that is still inside this square root that we have. From here, all of those are actually perfect squares, so I'm going to break this apart into the square root of the numerator, so 4x squared over the square root of our denominator. And our last step is to simplify down. So square root of 4 is going to be 2, square root of x to the second will just be a single x, and the square root of 25 will give us 5. Since I can't reduce 2 and 5 any further, that will be our final answer. All right, let's look at example 17. So in example 17, we have 36a over 4a to the third. Now what I notice here is that some of these are perfect squares, so I'm going to leave those alone, and some of these are not. So 36 and 4 are both perfect squares, so I want to leave that parts of the fraction, but a over a to the third can be reduced down. So if I have a over a to the third, I would subtract the exponents, and I'd get a to the negative 2. We don't want any negative exponents, so remember we can rewrite that then as 1 over a to the second. So when I'm reducing this down, all I'm really simplifying is the variable piece, and we end up with the square root of 36 over 4a to the second, all inside the square root. From here, 36 and 4 are both perfect squares, so I'm going to go ahead and break this apart. So I have the square root of 36 in the numerator over the square root of 4a squared. Square root of 36 is 6. Square root of 4a squared will give us a 2a. And then my final step is if I can reduce anything I want to, and 6 divided by 2 is equivalent to 3 over 1, and that a is still left over in the denominator. So I end up with 3 over a then. That is not a 9. Let's make sure that looks like an a. So 3 over a as our final answer. All right, let's look at example 18. So example 18 says 2 times the square root of 49x to the fifth over 4x to the third. Why don't you guys pause the video and do example 18 on your own first? Let's check example 18. Now I noticed that 49 and 4 are perfect squares, so I'm going to leave those alone. So I'm still going to have a 49 and then over the 4. But x to the fifth over an x to the third can be reduced down to be an x to the second in the numerator. And from here, I now have perfect squares. So I have a 49 x to the second in the numerator over the square root of 4 in the denominator. Notice this 2 that was in front is just going along for the right each time. So in the numerator here, I end up with 2 times 7x all over 2. So the 7x is coming from the square root of 49, x squared, and then the 2 in the denominator is coming from the square root of 4. Last step is to simplify anything down. 2 over 2 will cancel, and I end up with 7x then as my final answer. Okay, let's look at example 19. So example 19 says negative 5 times the square root of 162x to the third over 2x. Why don't you guys pause the video and try example 19 on your own first? So in example 19, what I'm noticing is that 162, 2, x to the third, and x, none of those are perfect squares. So let's simplify this fraction down. 162 divided by 2 will give us 81, and then x to the third over x will give us an x to the second. Now I actually have two perfect squares. So 81 is a perfect square. Square root of 81 is going to give us 9, and then the square root of x to the second will give us an x. The negative 5 is being multiplied, so our final answer then will be negative 45x as our final answer. What I'm noticing in all of these is that we ended up actually not having any square roots in our final answers. And mainly, I'm noticing that although I ended up with some fractions, none of them had a square root in the denominator. Now, this only happens in really nice cases. There could be times where we still end up with square roots, like we did in the first 14 examples. But if I end up with a square root in the denominator, we actually want to do what we call rationalizing this. So our last part of this video is going to talk about what happens if I have a square root in the denominator. So sometimes the denominator is not a perfect square. Oops, sorry. I don't know why that jumps. So sometimes the denominator is not a perfect square, so we have to do what we call rationalizing the denominator. To do this, what we're going to do is multiply by our fancy number 1. So our fancy number 1 is when we multiply by the same thing over the same thing. And the reason that I call this our fancy number 1, so same thing over same thing, is because anytime I have a number over itself, it reduces down to be 1, but it's fancier because we're strategically choosing what we want to multiply by. And in this case, we're going to strategically choose to multiply by something that will get rid of the radical in the denominator. So let's look at example 20. All of these say to rationalize the denominator, which means I should end up with no more square roots in the denominator. That's what rationalizing means. So we have the square root of 3 over the square root of 7. To get rid of the radical in the denominator, I would want to multiply by the square root of 7. Because if I take something and I multiply by itself, I'm going to end up with the square root of 49 then, from the 7 times 7. And 49 then is a perfect square, and I would end up with 7 in the denominator. And that's coming because I'm multiplying by what's already in the denominator. But to make this balance, I have to do the same thing in the numerator. And this right here, to circle it in green, remember, this is what we're calling that fancy number 1 that we have here. So root 7 over root 7, if I reduce that down, would be equal to 1. So I'm not changing anything since I'm multiplying by the number 1. But the reason we're multiplying by root 7 over root 7 is because in the denominator, root 7 times itself would give us the square root of 49, which would just give us 7 back. In the numerator, root 3 times root 7, I can multiply those. I get the square root of 21. That has no perfect squares inside of it, so I can leave the square root of 21 alone. But I have now rationalized because I have no more radicals in my denominator. And that's the key to rationalizing. So in this case, when we're multiplying by the same thing over the same thing, what we really want to use is that same thing is use the denominator here, so that I end up getting the square root of something that's a perfect square, and so they will end up canceling and getting rid of the square root. We can also do this with variables. So in example 21, we have the square root of 5 over the square root of 8x. Here, I want to get rid of the radical in the denominator, so I'm going to multiply by itself. So multiply by 8x, square root of 8x, so then I have to multiply by that on top. So here's our fancy number 1. When we simplify this down, since I have 2 square roots on top, I can multiply those and get 40x then, so the square root of 40x, over in the denominator, 8x times 8x would give us 64x squared. And this will work out well since 64 and x squared are perfect squares. This will reduce down to just be 8x. For the numerator, 40 actually has perfect squares inside of it, so if I factor 40, we get 4 and 10. So I'm going to reduce this a little bit more with the square root of 4 times the square root of 10x, so the x is still there. Square root of 4 is 2, so we get 2 square root of 10x over 8x. Last step would be to simplify anything that I can. So what that means in terms of a fraction is the same thing it meant in terms of multiplication. If stuff is outside of the square roots, then I can simplify those down. And if stuff is left over inside the square roots, that can be individually simplified. So in this case, the 2 things that I can simplify are outside of the square roots. So the 2 and the 8x. So to do this, 2 over 8 would give us 4. So I end up with a 4x in the denominator and a square root of 10x in the numerator. Now it's really tempting to want to say, ooh, I can cancel those x's. But I cannot, because the x that's in the numerator is inside of a square root versus the x in the denominator is not inside of a square root. So I cannot simplify this down any further. All right, let's look at our last example. It says 2x over the square root of 11. Why don't you guys pause the video and do example 22 on your own first. In example 22, we want to rationalize. So to do that, I want to get rid of the square root in the denominator. So I'm going to multiply by the square root of 11. So I need to multiply by the square root of 11 in the numerator. In the denominator, we end up with the square root of 121. And in the numerator here, since 2x is outside of the square root, I can't multiply it to the 11, so we get 2x times the square root of 11. Last step is to simplify the square root of 121, which would give us 11, so I get 2x times the square root of 11 all over 11. And the only stuff I could simplify is stuff that's outside the square root, and 2x over 11 will not reduce down, so that is our final answer then. So there's a lot of stuff in this first part of learning target 10B. We talked about how to multiply square roots and simplify, how to divide square roots and simplify, and how to also rationalize the denominator in case we ever simplify down a fraction and end up with a radical in the denominator.